Okay. It. Well, I'm feeling a little bit epic today, for sure. Okay, so last time I was reading this paper, I think. Yeah, reading this paper, and I ended it right here. So I'm going to continue reading this paper. Convolutional networks process image features with local convolutional kernel layer, local convolutional kernel layer by layer, thus are not effective for borrowing features from distant spatial locations. To overcome limitation, we consider attention mechanisms and introduce a novel contextual attention layer in the deep generative network. A novel contextual attention layer in the deep generative network. Illustration of the contextual attention layer first. Firstly, we use convolution to compute matching score of foreground patches with background patches as convolutional filters. Then we apply softmax to compare and get attention score for each pixel. Oh, interesting. So it sounds like they consider a background and a foreground. And they have two different attention mechanisms for each. Finally, we reconstruct foreground patches with background patches by performing deconvolution on attention score. The contextual attention layer is differentiable and fully convolutional. So, okay, interesting. I'll come back to that. To overcome this limitation, we consider attention mechanisms, which is novel contextual attention layer in the deep generative network. In this section, we first discuss details of the contextual attention layer, and then address how we integrate it into our unified in-painting network. Contextual attention. Contextual attention layer learns where to borrow or copy feature information from known background patches to generate missing patches. It is differentiable, thus can be trained in deep models, and fully convolutional, which allows testing on arbitrary resolutions. Match and attend. We consider the problem where we want to match features of missing pixels foreground to surroundings background. As shown in figure 3, we first extract patches 3 by 3 in background and reshape them as convolutional filters. To match foreground patches with background ones, we measure with normalized linear product. We want to match features of missing pixels foreground. The surroundings background. As shown in figure 3, we first extract patches 3 by 3 in background and reshape them as convolutional filters. Where we want to match features of missing pixels to surroundings. So, like, they want it to blend in. Is that what I'm hearing? We first extract patches 3 by 3 in background and reshape them as convolutional filters. What? Wait, okay, so there's novel contextual attention layer. In this section, learns where to borrow or copy feature information from known background patches to generate missing patches. Okay, yeah, that makes sense. Yeah, okay, that's how attention works. It is differentiable, thus can be trained in deep models and fully convolutional. Okay, yeah, sure. That's that's another aspect of that kind of thing. It needs to be differentiable. Thus can be trained in deep models and fully convolutional, as well as testing arbitrary resolutions. Ah, okay. Contextual attention layer. Okay, yeah. We consider the problem where we want to match features of missing pixels to surroundings. Oh, the missing pixels are the foreground. Oh my god, I'm an idiot. Okay. And the surroundings is the background. So this blue thing is the mask, if I'm understanding correctly. So in this section, we first discuss details of the contextual attention layer. Wait, why am I rereading that? So reshape those convolutional. So okay, we first extract 3x3 patches in the background and reshape them as convolutional filters. What does that mean? Reshape them as convolutional filters. I'm so confused. What? Conv for matching. Softmax for comparison. Yeah, I'm really not understanding this. Okay, match foreground patches with background ones. So do they like literally just like cut out like they just segment the image into like 3x3 things? What's the point of that? I'm so confused. We measure with normalized inner product, cosine similarity. Normalized inner product. Or just the inner product. I forget what this is. Wait, is it literally the dot product? What is that notation? Is that just dot product? I know it's also called the inner product. Is that like a thing that is a actual notation? Algebraic definition. Properties. Notation. Inner product. Okay, but where's the thing? This right here. So they just find the angle between the vectors. I am so confused what it means by reshape them as convolutional filters. So a convolutional filter is just a matrix, right? Or it can be represented as such. So what the heck does that mean? Also, why is it like the top one is like fat and then all these ones are like thin? Was it just like some guy was just like, hey, I drew enough lines. Okay, like that's really like tripping me up. Like this looks almost why is this bigger? Yeah. Yeah, okay. Do they overlap? Like that's what I'm not getting. I don't know. similarity of patch centered in background and foreground. Okay, so that's what this section is called. I just want to make sure I'm... Then we weigh the similarity with scaled softmax along x prime y prime minus dimension then we weigh the similarity with the scaled softmax along the x prime y prime dimension to get attention score. Is it just me, or like, are there like articles missing? Like, I feel like I'm going crazy. I don't know, like, get the attention score? The attention score? For each pixel, S star, X, Y, X prime equals a softmax. For lambda as a constant value, this is efficiently implemented as convolutional and channel-wise softmax. Finally, reuse extracted patches and deconvolutional filters to reconstruct foregrounds. Values of overlapped pixels are averaged. Where is figure 4? They don't talk about figure 4 until later, it looks like. Okay. As shown in figure 3, we extract patches in the background. In background. I really don't know, like, does it change the meaning, or I don't know. And reshape them as convolutional filters. What does that mean, reshape as convolutional filters? We extract patches? I'm going crazy. I'm crazy. Well, I guess I'll just continue reading and see if it makes sense. This is officially implemented. Okay, reuse extracted patches as deconvolutional filters to reconstruct foregrounds. Values of overlap pixels are averaged. Attention propagation. We further encourage coherency of attention by propagation. The idea of coherency is that a shift in foreground patch is likely corresponding to an equal shift in background patch for attention. The idea of coherency is that a shift in foreground patch is likely corresponding to an equal shift in background patch. Foreground. For example, blah usually have close value with... Dude, am I not reading the right version of this paper? Like, what is this? I'm gonna like look this up. Generative inpainting with contextual attention. I don't know. Is this? Jeez, I really hope so. Like I'm having such a hard time understanding this. It really is like. I feel like. Well, I tried. Oh my god. For example, usually have close value with. S star usually have... I'm so like... What is it? Is it actually saying something? Like, this should be plural, right? But I'm just so confused. Usually have close value with. Okay, I'm sorry, but like this is like really hard to understand. Usually have a so there's these two things. Oh, okay. I see. So they're assuming that it's like a smooth transition. To model and encode coherency of attention maps, we do a left-right propagation followed by a top-down propagation of kernel size k. Take right-left propagation as an example. We get new attention score with. Dude, who wrote this section? What the hell? Okay, the propagation is efficiently implemented as convolution with identity matrix as kernels. Attention propagation significantly improves in-painting results in testing and enriches gradients in training. Memory efficiency. Assuming that a 64 by 64 region is missing in a 128 by 128 feature map, then a number of convolutional filters extracted from backgrounds that a 64 by 64 region is missing in a 128 by 128 feature map. So that's wait. The feature map is the photo, right? Right? The number of convolutional filters extracted from backgrounds is that. Wait, I want to see if I can actually if I actually understand this. Okay, so the number of things extracted from the background. I'm going to get a notebook really quick. Be right back. So if I understand this, right, then what I should see actually maybe I can just open up Paint or something. I don't know. I'll see. Oh, I can put my notebook in my desk. I got a new desk. That's why I'm happy about it. Okay. Okay, so if I have something, what did I just do? It doesn't really matter. And then I have a square, right? I see why it's a rectangle now instead of a square. Okay. I'll stop roasting them. I'll stop roasting the authors. Okay. So, okay, this is actually not a great example. You know what? Done with this. I don't care. Okay, so we have, if I just change it to red or whatever, we have here. We have here. Okay, so going down, right? We're going to have, what is this? This is like, yeah. You're going to have, oh, okay. So you're definitely going to have, like, whatever this is, let's call it y. Y over 3. And then you're going to have another set of those, y minus 1 over 3. And then you're going to have y minus 2 over 3. And then with that, you won't be double counting any in this particular row. Okay, and then we're going to multiply that by the same thing with the x's. X over 3, blah, 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 dot, 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 dot. Right? And then we need to subtract something as well. So if I go ahead and new, okay. So we're going to subtract, so let's call this the whole. Let's call this h x. No, that doesn't even make sense. hy hx. Okay, so in this case, right? We have 64 by 64. Okay, we have 128 by 128. Okay, so we have y equals 128, x equals 128, hy equals 64 equals hx. Okay, so we have 128 over 3 plus 127 over 3 plus 126 over 3. And that's squared. Minus 64 over 3 plus 63 over 3 plus 62 over 3. Also squared. Okay, so what's that going to equal? So 128, I'm going to open up Python. Okay, so damn. Okay. 127 over 3. 26 over 3. Minus 64 over 3. Plus 65 over 3. I'm sure I am actually missing something here, but as long as it's in the ballpark, I'll be satisfied. 63 over 3 plus 62 over 3. That is not a thing. Oh, it's times times. Yeah, okay. 12. This seems like it's actually in the ballpark. Wait. Okay, it's like the right order of magnitude. Why is it like very off? I know, it seems like it's like really off, and I am very like weirded out by that. . Okay, what if I actually look at this region and then multiply it by 2, right? And that region is composed of this region, which has x equals, if this is 64, then that implies this is 32. This is 32. X equals 32. Y equals 64 plus 32. Oh, bless me. Oh, but then there's also the ones on the border that I don't end up counting. Are there like a lot on the border or something? 128 over 3. Or I'll just do 32 over 3. Ah! You know what? I'm just gonna assume that I understand it. Just move on. Because I have no idea what's going on. This may cause memory overhead for GPUs. To overcome the issue, introduce two options: extracting background patches with strides to reduce the number of filters, and 2, downscaling resolution of foreground inputs before convolution, and upscaling attention maps for propagation. Unified in-paging network. To integrate the attention module, we introduce 2 parallel encoders, as shown in Figure 4, based on Figure 2. Contextual attention layer. Man, this always reminds me of like Inuyasha. Ah, okay, so this layer is this guy, right? That's the refinement network. For visualization, okay. The bottom encoder specifically focuses on hallucinating contents with layer by layer dilated convolution, while the top one tries to attend on background features of interest. Output features from the 2 encoders are aggregated and fed into a single decoder to obtain the final output. To interpret contextual attention, we visualize it in a way shown in Figure 4. We use color to indicate the relative location of the most interested background patch for each foreground pixel. For examples, white center of the color coding map means the pixel attends on itself, pink on the bottom left, green on the top right. The offset value is scaled differently for different images to best visualize the most interesting range. Okay. Oh, interesting. So this guy depends more on over here, which makes sense. Yeah, okay, that makes a lot of sense. And this guy, and then these guys depend more on down here. Or just, yeah, in this direction. And this depends on itself, I guess. Interesting. What if you used attention outside? Wait, is that what they do? See, this is my problem, is that I don't understand what they're doing. Unified in-paging, okay. Well, the top one tries to attend to background features of interest. How features from two decoders are aggregated and fed into a single decoder to obtain final output. Oh yeah, okay. For training, given a raw image X, we sample a binary image mask M at a random location. Input image Z is corrupted from the raw image as Z equals X Hadamard M. In painting network G, concatenation of Z and M as input, and output predicted image X equals G Z of M. With the same size as input, pasting the masked region of X prime. Pasting the masked region of X prime to input image. Okay. We get the input. We get the in painting output. Concatenation of Z of M an output predicted image. Yeah, okay. Image values and output are linearly scaled to -1, 1 in all experiments. Training procedure is shown in algorithm 1. Okay. Well, G is not converged. Do for I equals 1 ... 5. Sample batch images. Yeah, okay. We evaluated the proposed in-painting model on 4 datasets, including places 2, slab A faces, slab HQ faces, DTD textures, and ImageNet. We show in Figure 5 that our baseline model generates comparable in-painting results with the previous state-of-the-art by comparing our output result and result copied from the main paper. No post-processing steps are performed in our baseline model, while image blending is applied to a result of 17. Yeah, okay, this is all just a butcha. Oh, here's the attention. Oh, interesting. Wow, that did really bad. Both of them did terrible. Well, that did really good. Yeah, that's fantastic. At least I think so. Yeah. Oh, I see. Oh no, but okay, yeah, that's actually great. That's really impressive. Decent, I guess. It's interesting how it just copied the thing. Yeah. Huh. Range of other spatial attention models including appearance flow and spatial transformer network. Image and painting. For appearance flow, we train on the same framework, except that the contextual attention layer is replaced with a convolutional layer. Convolution layer directly predicts 2D pixel offsets as attention. Interesting. Huh. I'm thinking. Thinking Lincoln. That's what they called me back in 1865. This is so interesting. I do want to read up on these GANs. Ah. Oh no! No! Oh, where's my cap? Oh, there it is. I guess maybe I should just read about this model, or not read about it, but look at the implementation. Because I really do want to understand it. I mean, this is like the state of the art as far as I know. I'll just look it up. This this really the state of the art? An image in painting? A one-stage model utilizes dense combinations of dilated convolutions to obtain larger, more effective receptive fields. Recover large ranges in an incomplete image. Except for frequently used VGG feature matching losses, we designed a novel self-guided regression loss. We're concentrating on uncertain areas and enhancing semantic details. Besides, we devised a geometric alignment constraint item to compensate for the pixel-based distance between prediction features and ground truth ones. We also employ a discriminator with local and global branches to ensure local-global contents consistency. To further improve the quality of generated images, discriminator feature matching on the local branch is introduced, which dynamically minimizes similarity of intermediate features between synthetic and ground truth patches. Extensive experiments on several public datasets demonstrate that our approach outperforms current state-of-the-art methods. Okay. So, is this the state-of-the-art? Did I find the state-of-the-art? Wow, this is true. This is amazing. Wait. No, wait, hold on a second. What? Is this the ground truth or is this the result? Okay, this must be the ground truth. Yeah, I'm like, what? What is the state of the art? This is very unclear to me still. Ten papers that I have to read. This is November 30th, 2020. How does deconvolution work, actually? That's something that I am not super clear on, but I definitely I need to understand that, because that is like a key concept in this whole thing. Okay. Deep fill was you? Yeah, Izuka. Edge connect. Lines first, color next. Interesting. Deep fill V2. Oh. So that wasn't the state. I just wasted all my time on some bullshit, non-state-of-the-art BS. Free! Oh my god. This is the worst webpage ever. Alright, I am what? Dum dum dum. Dum 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 dum. Wait, what? Wait, hold on a second. What? Okay, well this is pretty state of the art apparently. I am very glad I looked this up because even though I feel stupid and I put my stupidity on display, I am humbled. Okay, I have things to look at. Ethics. What is this? What is this? What? What? Wait, the virtual. Is based on generative adversarial. Interesting. Huh. Huh. Interesting. I don't know. Is it good? I will keep that in the background. That's interesting. Huh. Okay. Context-aware image in-painting model which adaptively integrates global semantics and local features in a unified image generator. Semantic learner and image generator are trained in an end-to-end manner. Its ability to learn and leverage semantic priors. It achieves the state-of-the-art It achieves state-of-the-art. Okay, that's quite a tall, very interesting statement. Okay. I mean, fuck, if this is true, this is pretty solid. What is this called? Context aware. Maybe there's a GitHub for it. What is AAI-20? I assume you et al. That's this one, right? Yeah. Okay. Um. This is fascinating. Oh wow, RFR is pretty solid in this particular case. Interesting. I would be super interested in trying this out. Yeah, well. I am going to put this on the back burner because this looks incredibly interesting. Anyway. I will see y'all later.